Of particular interest for many emerging implementations of quantum technologies, such as quantum computing or quantum cryptography, are two-level quantum systems. These so-called quantum bits, or qubits, named in analogy to a classical bit, can be realized using different physical systems such as electronic spins, energy levels of trapped ions, or the polarization of photons. Unlike classical bits, however, multiple quantum bits can be prepared in a quantum entangled state, giving rise to properties that cannot be explained with local hidden variable theories. In this experiment, we will work with photonic qubits, photons that are entangled in their polarization degree of freedom. Entanglement is exploited in many quantum technological applications such as quantum cryptography, communication, and also computing. In using this physical system, we will demonstrate the violation of the so-called Bell inequality. This inequality, derived by John Stuart Bell in 1964, proposed a test that allowed to accept or refute the postulates of Einstein, Podolsky, and Rosen, in short EPR, which is widely known as the EPR paradox. This is a thought experiment which the three physicists used to try to show that quantum mechanics cannot completely describe physical reality. For the actual experiment, we will rely on the CHSH test criterion, named after yet another group of physicists, Clauser, Horn, Chimney, and Holt, which translates Bell's inequality into a more experimentally accessible setting. And this, by the way, is also one of the main contributions that Clauser received the Nobel Prize in Physics for in 2022. So before we go into the actual experiment, let's look a bit more at the physical foundations. Generally, the state of a physical system is defined by a vector in Hilbert space. When considering a single qubit, in our case a photon and its polarization, the corresponding Hilbert space has a dimension of 2, such that each polarization can be expressed as the superposition of two orthogonal basis vectors, for instance horizontal and vertical. For a single qubit, this vector representation of the polarization state of a single qubit closely relates to the concept of Jones vectors used to represent polarization of classical light fields. Now, in the next step, we want to consider two qubits, meaning two photons, which are possibly entangled in their polarization degree of freedom. The corresponding Hilbert space for the two qubit case is obtained from the tensor product of the two single qubit spaces. As a result, we have to consider a four-dimensional Hilbert space now. We can now distinguish two important cases. The first option is the two qubit state can be directly written as a product of single qubit states. These types of states are referred to as separable or product states. In this case, no entanglement exists between the two qubits. The second case is that the two qubit state cannot be factorized into a simple product of single qubit states, and in this case, two or more possible configurations of the polarization state are in a coherent superposition, and the total state is said to be entangled. Most importantly, in the case of a separable state, the measurement on one photon cannot influence the second photon in case both are spatially separated. This means both photons can be described locally. In contrast, for an entangled state, a measurement on one photon of the pair will always affect the outcome of a measurement performed on the second photon, even if they are spatially far separated. This spooky action at a distance, as Albert Einstein famously phrased it, implies that quantum mechanics does not follow local realism. Furthermore, the immediate effect of the measurement of the first particle on the measurement outcome of the second particle, even though they're separated arbitrarily far, seems to imply that information is exchanged faster than the speed of light. Now, in particular, this prediction of quantum mechanics was challenged by Albert Einstein together with co-workers Boris Podolsky and Nathan Rosen in 1935 in a thought experiment known as the EPR paradox. They did not reject the formalism of quantum mechanics. However, they stated that the theory is not complete. Briefly summarized, their assumptions were that a correct physical model should always show completeness, realism, and locality. As such, they postulated that the predictions of quantum mechanics, which for instance implied non-locality, are a sign that hidden variables exist, which, when considered, lead back to a local model. At the time of the publication of the EPR paradox, no experimental method existed to verify if a local hidden variable theory is correct or if quantum mechanics is inherently non-local. A solution was developed by John Stuart Bell in 1964, who derived an inequality that can serve as a test criterion for local hidden variable theories. If the so-called Bell test is carried out on a quantum system that follows a local hidden variable model, the test criterion will be bound to a certain quantifiable value. In case this value is exceeded, meaning the Bell inequality is violated, the physical system does not obey local realism, meaning the non-local quantum description would be correct. Now, in our experiment, the investigated physical system will be 2 photonic qubits, which are prepared in a maximally entangled state. Since the initial proposal from Bell is experimentally hard to implement, in this demonstration we will measure a different inequality proposed by John Clauser, Michael Horn, Abner Shimony, and Richard Holt, so CHSH, 5 years later. In the CHSH inequality, we have a test parameter S that is bound to 2, in case the examined physical system follows a local hidden variable theory. It is determined by several correlation measurements, which signifies a simultaneous measurement on each separate qubit of the entangled state at different locations. In our case, these measurements will be projections onto a particular polarization basis stage, which practically means that both photons are sent through 2 separate polarizers and afterwards detected by a single photon detector. In order to correlate the 2 spatially separated measurements, the arrival time of the photons at both detectors is compared. So the core components we will use in this experiment are a source of polarization entangled photons, 2 linear polarizers, which we use to set different polarization states, and then 2 correlated single photon detectors here, which are time correlated. So practically the normalized correlation value for a particular setting of polarizer positions can be determined in an experiment by measuring the coincidence count rates. Yeah, so this is the experiment we will carry out now. So we switch now on the laser and guide our photons through the polarizers, through the fibers to the detectors, which we will do now. So now the system is automatically scanning through different polarization bases by rotating the linear polarizers and detects the coincident count rates shown on the display. Yeah, and now we have measured an S value, which is of the value 2.59, which clearly is larger than 2. So in case the local hidden variable model would be correct, the maximum value we could have measured would be 2. Yeah? Therefore, our experiment shows that the local hidden variable model does not explain our measurement results. So of course, there can still be criticism to this particular experiment. There's the so-called locality loophole. This occurs whenever communication between the measurement settings of the 2 observers, in our case the 2 detectors, cannot be excluded. So the usual solution would be to increase the separation between the measurement sites. Also, a rapid and random change of the detection basis can be used in addition. Yeah? And then there's also the so-called detection loophole. If the measurement efficiency is low, it could be that the whole ensemble behaves according to a local hidden variable model, while the measured particles do not, since with the low efficiency detectors, we don't catch all of the photons, for instance. Yeah, while we cannot route all these loopholes in our experiment, more elaborate experimental setups have done so in the past, such that there is a high confidence in the scientific community that the Bell inequality can actually be violated with this type of measurement.